All right, guys, so I'm recording, so I just want you to know that. 2.4, continuity and one-sided limits. It says in mathematics, the term continuous has much of the same meaning as it has in everyday usage. Informally, to say that a function f is continuous at x equals c means that there is no interruption
No interruption.
on the irony in that.
I like that.
Hey, that's okay. Yes, she is getting fingerprinted this morning. Yes, but I think it's at home. Which is fine. That's what they're supposed to do today. Um, I thought you told me to send it to somebody. I don't remember, to be honest. No, I put it in the courier. Yeah. I don't have one. Doing notes with them. Yeah. Right. Well, I mean, she's off all day today. Can she go home and get it and then come back? Well, I mean, that is so dumb because I did send it through the courier. Yeah, I mean, we can figure it out. If y'all want to do that, that's fine. It'll literally take 2 days.
Yeah, what person got it too at the same time? Personally, so.
Okay. Yeah, she was supposed to have an appointment at 9:30. Well, tell her worst case, you can fax it within the next 30 seconds. All right, all right.
Did you say no interruption?
No interruption of the graph of f at c. That is, its graph is unbroken at c. There are no holes, jumps, or gaps. Below are 3 values of x at which the graph of f is not continuous. And I'll show you that graph in a minute. I just didn't put it on here. At all other points, sorry, what? Oh, sorry. At all other points in the interval AB, the graph of f is uninterrupted and continuous. All right, so let me show you this. So just to save you some time, here's a hole where it's undefined. Here's a jump. And then again, if you look, 3 conclusions exist for the graph of f is not continuous at x equals c. So this one is not defined. This one does not exist. And then f of x does not equal f of c. Okay. So holes, jumps, can't have those. Everybody good? Yes. So that's the figure that you're looking at. If you want to put it on page 90, you can do that. So in those figures, it appears that continuity at x equals c can be destroyed by any one of three conditions. So the first condition, the function is not defined at x equals c. The limit of f of x does not exist. DME is does not exist at x equals c. And the limit of f of x exists at x equals c. That is not equal to f of c. So if none of the three conditions is true, then the function f is called continuous at c. So then the definition of continuity or continuity of points, a function f is continuous at c when these three conditions are met. F of c is defined the limit as x approaches c of f of x exists. The limit as x approaches c of f of x is going to equal f of c, that direct substitution that we talked about. Is everybody good with this page? Okay. Continuity on an open interval. A function is continuous on an open interval AB when the function is continuous at each point. In the interval. A function that is continuous on the entire real number line of negative infinity to infinity is everywhere continuous. We're going to consider an open interval I that contains a real number c. If a function f is defined on I, except possibly at c, and f is not continuous at c, then f is said to have discontinuity at c. We're going to talk about it. I know, we're going to talk about it. So remember, discontinuities are like holes in vertical asymptotes. It's where the graph, you have to pick up your pencil. So that's all it's saying. All right. So again, consider an open interval I that contains a real number C if the function f is defined as I, except for defined on I except for possibly at C, and f is not continuous on C, then f is said to have a discontinuity. So right. So if it's not defined, it's a vertical asymptote or a hole, a gap, anything like that. So that's all it's talking about. So there are two types of discontinuities. There are removable and non-removable. And these are easily like to distinguish between. So don't stress out about it. It's really easy. Right. A discontinuity at C is called removable. When f can be made continuous by appropriately defining or redefining f of C. For instance, the functions below, and I didn't put the figures on there again. Page 91, I'll show you those so you guys can see them. This is more complicated than it needs to be. All right, so here's the first one. It's a hole with removable discontinuity. When we do it algebraically, it will be much easier to see, okay? This one has non-removable because it's got the gap. And this one has removable because you can add that point into there. So I can redefine that function. And when it means redefine, you might have a vertical asymptote to start with, but you can mark it out. Okay, we'll talk about it in a minute and I'll show you everything algebraically. All right. So this says discuss the continuity of each function. So 1 over x. Remember, anything that you, like if you factor it, whatever you mark out is a whole. Anything left in the denominator is a vertical asymptote. If you cannot factor it, then it's going to be non-removable. Okay, so like 1 over x has that x in the denominator. That means there's a vertical asymptote at x equals 0, because we can't define this function at 0. We can't divide by 0. Is everybody okay with that part? It is non-removable because I can't rewrite this function or define it any different. So basically, if I could factor it out and cancel off that x and not have that denominator anymore, that would be a removable because I removed it from the situation. Okay, and we'll get one of those in just a minute. So the continuity, we have to disclude. We have to not include 0. So our continuity, this function is continuous from negative infinity to 0, 0 to infinity. I don't, but you can. I'll tell you what this is. I'm sorry, I don't normally do this. That phone call was Miss Craver now, Miss Davison. My mom is trying to be a sub. Her last day of work was yesterday. She's retired now, and she wants to still do some work. So she wants to be a sub. So she's been trying to get with the county. She had an appointment to do her background check and fingerprints today, and they don't have her paperwork. And I sent it through the courier. And we both know I sent it because Miss Davison told me where to send it. And she said, also make a copy because they like to lose things. So here we are. So if she comes in here, I might have to run home, which is right there, and get that paperwork and come back. So if she comes in here, that's what's happening. All right. Okay. So does everybody understand why it's continuous, but we exclude zero? Zero is a vertical asymptote, so it doesn't count. So everybody good? All right. So on this next one, right now, we're going to have, it looks like a vertical asymptote at positive 1, right? Because that would give us a 0 in the denominator. But we can factor the top into x plus 1, x minus 1. And we can remove that discontinuity. Does that make sense now? So you can see how you mark it out. What does this cause? Okay, so it's still, this hole is still a point of discontinuity. So we have a discontinuity. At x equals 1, because that would cause a 0. But this time, it is removable because we can mark it out. So then when we graph this function, it's going to be a line. It's going to be a line, which means that it's continuous the entire way because we removed that discontinuity. Uh-huh. Mm-hmm. So on the other one, we couldn't remove that discontinuity, so we had to include it in our interval, our continuous interval. On this one, we could remove it, so we don't have to include it. So it's just negative to positive infinity. Is everybody good? Okay, so that's all it is. So the next one, I had to graph this one, and I'm going to go ahead and show you what it looks like graphed. I'm going to make it a little bit bigger because I don't like the little bitty graph paper. I want you to be able to see it. All right. So less than 0, we're going to graph x plus 1. Greater than 0, we're going to graph e to the x. And this is your 0. All right. X plus 1 is less than or equal to 0, so it's going to be closed on the zeros. So this graph starts at 1 and it's closed. And it should go up 1 over 1, but we don't graph it on this side, so we're going to go down 1 over 1. Is everybody good? Well, you can plug in values, but if you have your calculator, it's an exponential function. So it's going to be, it goes up quick. So e to the x, what I did, I don't know if I'm looking right here, is put it in my calculator. And then I looked at my table, but I got to change my table set. Sorry, y'all. And at 0, it was 1, which is already there. At 1, it was 2.7. So 1, 2.7. Then at 2, it was 7.3, which is way up here. 1, 2, 3, 4, 5, 6, 7.3, something like this. So do I have any points of discontinuity? No, I don't have any holes. I don't have any gaps. I don't have anything. So this has no discontinuities. Which means it's continuous from negative infinity to positive infinity. All right. Look at your next one. I'm going to graph this one so you guys can see it. You should know what a sine graph looks like, even if you're not sure. Even if you're not sure where it's at, you should know that it's like a wave. And you should know that there are no points of discontinuity. So when you graph this, again, the difference in sine and cosine, sine goes through 0, 0, cosine does not. They're the same curve. It's just where they start that's different. I don't know what's happening over there. So this is a continuous graph with no discontinuities. So it's continuous on the all real negative to positive infinity.
So this continuous will always be negative infinity to positive infinity?
Say it again.
Is this continuous will always be negative infinity to
Mhm,
positive?
mhm. The only time that you'll ever have anything different is when you actually have a discontinuity point. Okay, is everybody good? All right. One-sided limits and continuity on a closed interval. To understand continuity, on a closed interval, you first need to look at a different type of limit called a one-sided limit. So I kind of hinted to this yesterday when I said those ones that increase or decrease or go opposite without bound. Okay, you guys understand what I'm talking about? That was when you were coming to a specific point. Now with your one-sided limit, you're going to look at just the left side or you're just going to look at the right side. Okay, so for instance, the limit from the right or the right-handed limit means that x approaches c from values greater than c. This limit is denoted as, is written the exact same way. So the limit as x approaches c, that they put a little plus sign. So the plus sign means right of f of x equals L. Similarly, the limit from the left or left-handed limit means that x approaches c from the values less than c. So it looks exactly the same. Limit as x approaches c, but this time you're going to put a little negative of f of x equals L. So that's the difference. So if you just see a number, it's normal. If you see a number and a little plus sign, that means just from the right, and a negative means from the left. And those numbers can be completely different. So now what's happening is it's taking account in those graphs or those discontinuities. So be ready for that. Those without bound. So if they both point up, if we're coming from the left, it goes to positive infinity. If we're coming to the right, it goes positive infinity. If they're opposite of each other, from the right, it goes to positive infinity. From the left, the other way around. I'm doing it backwards for you guys. It goes to negative infinity. So everybody got it? Don't stress. It's really easy. Okay, quit with those eyes. One-sided limits are useful in taking limits of functions involving radicals. For instance, it should say instance. If n is an even integer, then the limit as x approaches 0 from the right of the nth root of x is going to be 0. Okay. I'll show you what that looks like. Doesn't matter what we put in. If I put in square root of x and I graph it, we're literally following the graph from right to left. So we're coming from the right, okay? When it gets to 0, what is the point that it hits? 0. That's exactly where that's at.
So, if you put like a continuous thing, would it be like 0 to positive?
This one would be.
Yeah.
Yeah. All right. Find the limit of f of x equals square root of 4 minus x squared as x approaches negative 2 from the right. So we're looking for the limit as x approaches negative 2 from the right with the square root of 4 minus x squared. I'm going to graph this on my calculator, but then I'm going to sketch it on your paper so you guys can see it too. Okay. So this is a half circle. Okay. So it looks like this. It's a really crappy half circle, but you get the idea. So if we follow this graph from the right to negative 2, what is the value that we get to? Basically your y value. That's it. Okay, no, you're fine. So you're going to look at the graph and you're going to go from the right. So start on the right side and basically trace that graph till you get to the value it's looking for, negative 2. Okay. What would be the value if you approach, like if it was the limit of 0? So x approaches 0 from the right. That's it. Okay. Don't make it more complicated than what it is. Everybody good? One-sided limits can be used to investigate the behavior of step functions. Also going to teach you how to put those in the calculator so you can see them. Common type of step function is the greatest integer function. And remember, that's when you have the double bracket and x. This is the greatest integer n such that n is less than or equal to x. So I'll give you some examples in just a second. All right. If I told you to find the greatest integer of 2.5, it's the greatest integer less than that number. So the first whole number less than 2.5, which would be 2. Do what?
I was going to ask why people do this.
Yeah, it's got to be a whole number. That's all. So same thing here. What's your greatest whole number? I'm sorry. Your smallest whole number. Yeah, your greatest whole number is smaller than negative 2.5. Negative 3. It's got to be smaller than negative 2.5. So you got to think backwards with negatives. That's why they gave you a negative example. Is everybody good? All right, real quick before, you're fine, you don't have anything to write down. I just want to show you on the calculator how you can do this. If you go to math, like you're going to absolute value, you go over to num. Number 5 says int. That's your greatest integer function. So if we put in that negative 2.5, it'll give you that negative 3. Okay, so if you're ever confused about that, you can graph it the same way. So if you wanted to graph the greatest integer function, math, integer of x, it'll do that graph for you. It's called a step function because it looks like steps. Is everybody good? All right. So that's what we're going to do on the next part. It says find the limit of the greatest integers function. I just graphed it for you, but I'm going to make it a little bit bigger so that you can see it. So what's going to happen is at every integer, you're going to have a closed point. So 0, 0 be a closed point. But then you go to 1 with an open point, and that's what makes that horizontal line like you see here. Okay. So then you step up to 1, 1. Draw a line over to the next integer, but it's an open circle. 2, 2. Open circle. Same thing on the bottom, -1, -1, open circle. Looks like this. Very good. All right. So it says find the limit of the greatest integer function. So the limit as x approaches 0 from the left. So we go from the left. We look at 0. What is our function? Be careful on this one. Okay. As we go from the left, the first time that we're going to touch 0 is with this little line right here, which is -1. Now I'm going to go one step further, and I know it doesn't ask you to do this, but we're going to go from the right. It would be 0. Okay, so from the right, the first time that we touch 0 would be right here. Okay, so again, this is 0 from the left. This one is 0 from the right. I hate step functions. I think they're really awkward to look at. Once we get like real functions, y'all, this is super easy. It's super easy. All right. Just to take it another step further, this is discontinuous at 0 because the left and the right limits are different. Also because it's a gap. So it's discontinuous at a lot of places on here. But again, that's a way to tell about a discontinuity is when the limit from the left and the limit from the right are two different numbers. Okay. When the limit from the left is not equal to the limit from the right, the two-sided limit does not exist. So we talked about that yesterday, that when it's unbounded, it doesn't exist. But if you specify which side, it will then become into existence. The next theorem makes this more explicit. The proof of this theorem follows directly from the definition of a one-sided limit. So theorem 2.10, let f be a function and let c and l be real numbers. The limit of f of x as x approaches c is L, if and only if. The limit as x approaches c from the left of f of x is L. And the limit as x approaches c from the right of f of x is also L. So again, the limit will exist if from the left it's the same number as the right. It will not exist if it's on the other thing, but you can find it if you just do the right or just do the left, okay? So the concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. Basically, a function is continuous on a closed interval when it is continuous on the interior of the interval and exhibits one-sided continuity at the endpoints. This is stated formally in the next definition. All right. A function f is continuous on the closed interval AB when f is continuous on the open interval AB. So the only difference is closed means bracket, open means parentheses. That means the limit as it approaches A from the right of f of x will just be a direct substitution, f of A. And the limit as x approaches B from the left of f of x will also be direct substitution. The function f is continuous from the right at A and continuous from the left at B. Is everybody okay? Similar definition can be made to cover continuity. Sorry, you can't really read that. Continuity. On intervals of the form open A, closed B, and closed A, open B. I don't feel like there's any easier way to say that. That are neither open nor closed. So this interval is not fully open, nor is it fully closed. Or on infinite intervals. So for example, if we had the function the square root of x, it is continuous on the infinite interval from 0 to infinity. So that's where it's showing you closed but open because we never include infinity. Okay, so it's not a fully open and it's not a fully closed interval. And the function f of x, sorry, g of x, it doesn't matter. It's not any point. Just telling you it's a different function. Equals the square root of 2 minus x. Because this function is continuous on the infinite interval. Negative infinity to closed positive 2, not negative 2. All right, so you know the square root of x starts at 0, 0 and moves to the right. The only thing about this one, the reason they use this one, square root of 2 minus x, is it flips it over because it's a negative. So they're trying to show you that it goes to the negative infinity. That's the only reason they use that function. It didn't come from anywhere. They're just trying to give you a left side. All right. So discuss the continuity of f of x equals square root of 1 minus x squared. When we graph this, it's going to be a half circle. It should touch 1 up there. Sorry, y'all. A little bit fatter circles. So there's a couple things I'm going to write, and you know that. It doesn't tell you anything. When it says discuss the continuity, these are the things that they want. So the first thing, what is the domain of this function? Included or excluded? Negative 1 to 1. So there's your closed interval. I'm just kind of writing points, so we're good. At all points in the open interval, negative 1 to 1. Now, this part you don't have to write. I'm just showing you where it's coming from. The continuity of f follows your theorems 2.4 and 2.5. That was a little while ago. So that is these theorems right here. The limit as x approaches negative 1 from the right of the square root of 1 minus x squared. So let me show you that real fast. Got it right here. I can get my paper to be apart. We had the limit of a, so that first part right there from the right, we're just plugging in a to find the limit. So if we plug that in, 1 minus 1 is the square root of 0 or 0. So by direct substitution, we know that the limit of negative 1, x approaches negative 1 to the right is going to be 0. Then we do the limit as x approaches b from the left. Our b value is positive 1 from the left. We can use direct substitution. So plug in your 1 again, which gives you 0. This statement tells you that it's continuous from the right. Again, you don't have to write all of this. I'm just trying to define it for you. This tells you it's continuous from the left. So from all of this information, this is what you need to know. F is continuous on the closed interval -1 to 1. What I would need to see would be this right here. Okay. The other part is just explaining where the 1 and the -1 came from. Does everybody understand that? So if they give you this function, you have to find your domain to be able to do these two things. Got it? All right. So again, what would I need to see? This part right here. All right. The next example shows how a one-sided limit can be used to determine the value of absolute zero on the Kelvin scale. On the Kelvin scale, absolute zero is the temperature 0K. Although temperatures very close to 0K have been produced in laboratories, absolute zero has never been attained. In fact, evidence suggests that the absolute zero cannot be obtained. How did scientists determine that 0K is the lower limit, and that's in quotations, of the temperature matter? What is the absolute zero on the Celsius scale? So they give you this formula. This just did not come out of nowhere. V equals 0.08213 T plus 22.4334. Where V equals volume and T equals temperature in degrees Celsius. All right, so it asks, how did science determine 0K is a lower limit of the temperature matter? So we need to solve for T. We need to get T by itself. So the way we do that, subtract the 22, divide by the 0.08. So I'm going to do that all at one time. T equals, we're going to take that volume and we're going to subtract 22.4334, and we're going to divide by 0.08213. Again, because we're trying to look for the limit, the lower limit, that's where the quotations come from, the lower limit of the temperature. So we're going to look for the limit as x approaches 0 from the right of T. We can do direct substitution. And we can do 0 minus 22.4334 over 0.08213. Again, it's asking what is the absolute zero on the Celsius scale. This gives us a negative 273.15. So what that tells me, absolute zero on the Kelvin scale, remember which was 0K, is going to be approximately negative 273.15 degrees Celsius. All right, so let's look real fast. This is what this is going to give you. It's going to give you this crazy line where all the way under, I zoomed fit so that I could see it. I'm gonna pull it back up. Why would we look at the limit as 0 approaches from the right? What are we talking about? What is our x value in our x value in our problem? Not that. We're looking at it as approaches 0, but what does actual x represent? When I put it into my calculator and I have that x up there, what did that x take the place of? Which is, can we have a negative volume? So why would we look from the left? Does everybody understand that? So I want to make sure you understand every aspect. Why did we solve for T? Because we were trying to get it in Celsius scale, so we needed temperature. Okay. Why did we go from the right? Because volume is positive, so we're going to look from the right. So everybody get? All right. Flip it over. Told y'all it's a long section, and I apologize. I think I'm going to take a note quiz today. In section 2.3, you studied several properties of limits. Each of those properties yields a corresponding property pertaining to the continuity. If you did them, you get 100, and if you don't, you do 0. For instance, theorem 2.11 follows directly from theorem 2.2. Theorem 2.11, properties continuity. If B is a real number and F and G are continuous, at x equals C, then the functions listed below are also continuous at C. The first one is a scalar multiple. Where would have, not B times G, where we'd have like B times F. We went over these yesterday, right, with our sine, cosine, trig functions. Okay, so same thing. Scalar multiple just means you multiply it by a number. I'm going to go down to number 3, would be your product, F times G, you're multiplying them together. We did sum or difference, which would be you just add them together or subtract them, so plus minus. And then we talked about your quotient, which was F over G, but G of C cannot equal 0 because we can't divide by 0. I know it's a lot. I'm sorry. The below list summarizes the functions you have studied so far that are continuous at every point in their domain. So these are functions that have 0 discontinuity. There's not going to be any discontinuity. And that would be polynomials. Polynomials are just bigger than the first degree. Okay, so 4x to the 5th minus 3x cubed minus 4, blah, blah, blah. Those are polynomials. Rationals. Radical. I'm just going to write trig. If you want to write trigonometric, that's fine. And then exponentials and logs. If you think about those 4 things at the top, the scalar multiple, the product, the sum, the difference, the quotient, by combining those with this list, you can conclude that a wide variety of elementary functions are continuous at every point in their domains. Composite functions are when we put them inside of each other. If G is continuous at C and F is continuous at G of C, then the composite function given by F, remember that's an open circle of G of X, is going to be the same thing of F of G of X is continuous at C. So it doesn't matter which way you write it. So it's either the fog or it's the other one. We got out of here 56, right? Okay. It's like this. F of G of X equals F of G of X. It's squished up in there. It's okay. Is everybody good? All right, testing for continuity. Describe the interval on which the function is continuous. So you're going to need these. Okay. F of X equals tan X. If you remember, tan looks like these little squiggly lines. That's not the best drawing, but it'll be okay. At X equals pi over 2. Plus n pi. That is something you probably should need to know. Got it? All right. So what that means is the intervals that it's continuous. Tan is a really weird one because it's going to have multiple intervals. It is continuous from negative 3 pi over 2 to negative pi over 2. Then it picks back up to negative pi over 2, pi over 2. So basically your x's are what you're looking at. It's always going to be pi over 2 for your y's at this point. And then it stops and it picks back up again, 3 pi over 2. Because it has so many vertical asymptotes. So tan is the really weird one. Yes. I think I said it, but didn't write it. Okay. G of X equals sine 1 over X when X does not equal 0 and 0 when X is 0. 1 over X is not continuous at 0. So at X equals 0, the limit does not exist. Again, because we have a hole. So that means G is continuous on everywhere else. Negative infinity to 0, 0 to infinity. So everything but that 0. All right. It's because even if you plug in 0 for sine 1 over 0, it will not work. Yes. Okay. So h of x, x sine 1 over x when x cannot equal 0, and 0 when x is 0. It's sort of the same thing, but it's not. Okay. Here's the difference. This x right here makes a difference. Does everybody understand that? That's the difference. So we learned, and when I was doing this, I was like, we learned squeeze theorem. I don't remember it. It's theorem 2.3. We did learn that. It's okay if you forgot it. But what it says is that the negative absolute value of x less than or equal to x sine 1 over x is going to be less than or equal to the absolute value of x. And again, x cannot equal 0. I'll go back and show you that. It's on our last set of notes, I think. Yeah. The limit as x approaches 0 of h of x is going to be 0. So you'll just have to go back and look at your squeeze theorem, and that's exactly where, here it is. It was on the last one. It's not 2.3, it's 2.8. 2.8. Sorry about that, y'all. So I'm gonna try to show you that at the same place. So it said h of x is less than or equal to f of x less than or equal to g of x. If the limit of c of h of x is L and limit of c for g of x is going to be L, then it's going to go to L. So basically both of these limits go to 0. So this one is 0. It's quite awkward, but we've already done it like once. Okay, so just watch that. All right. I want to try to at least finish this page, okay? And maybe the top of the next one a little bit. This is, I'll just fill in the blank. There's nothing here. If f is continuous on the closed interval AB and f of A does not equal f of B, and K is any number between f of A and f of B, then there is at least one number C, should say NAB, sorry about that, y'all, such that f of C equals K. The intermediate value theorem tells you that at least one number C exists, but it does not provide a method for finding C. Such theorems are called existence theorems. By referring to a text on advanced calculus, you will find that a proof of this theorem is based on the property of real numbers called completeness. But we don't do that. The intermediate value theorem states that for a continuous function f, if x takes on all values between a and b, then f of x must take on all values between f of a and f of b. Sorry, y'all. Try to make it good for you. The intermediate value theorem guarantees the existence of at least one number C in the closed interval A to B. There may, of course, be more than one number C such that f of C equals K. And we're going to go over the intermediate value theorem. We're just throwing all this information out at the beginning. And again, as shown in the figures on page 97, a function that is not continuous does not necessarily exhibit the intermediate value property. For example, the graph of the function shown in figure 2.36 jumps over the horizontal line, y equals K. And for this function, there is no value of C in AB such that f of C equals K. So I want to get this one paragraph completed and then we'll be done, okay? That's all I want to do. And then we'll do the application of the intermediate value theorem tomorrow. It can be used to locate zeros on a function that is continuous on a closed interval, specifically if f is continuous on the closed interval AB, and f of A and f of B differ in sign, then the intermediate value theorem guarantees the existence of at least one zero on f in the closed interval AB. And then we'll stop there. Again, no homework, no homework.